All right, let's settle down. Let's get started. It would help if I activated the screen. There we go. All right. So today we're going to do our full bore start to finish comprehensive mix design example. So if you recall, on Thursday of last week, we sort of went through the procedure start to finish step by step. And so today we're just going to use it. Okay. One thing I'll mention is that the mix design procedure, obviously based on the lecture on Thursday, requires the use of a lot of tables and charts and things like that. What I will tell you is that that information will be given to you on an exam. So for the purposes of preparing a formula sheet, you do not need to waste space on your formula sheet with like the F-factor table or table 7.1 or table 7.4 or whatnot. You don't need to do that because it will already be provided on the exam. I don't want you to waste space on your formula sheet with that. I was hoping to get lab assignments 4 and 5 graded by today. It just didn't happen, so that'll probably be a little bit later this week. But I have to get it done by next week, because next week we're going to do our mix design demonstration. So the way that lab will work next week is that Patrick and I will do a mock-up demo for you for the concrete lab. In other words, we'll show you how to do the slump test, the air content test, the temperature test, which the temperature test is really easy. Show you how to cast the cylinder, show you how to cast the beam, because you're going to do a lot of casting. So we're going to show you how to do that in that lab, so that when you come back the following week, we're going to do it. Okay. Today's lab, however, we're going to get to break stuff. We're going to break the cubes that we cast from the prior lecture, or from the prior lab. Sorry, from the lab last week. So last week you cast those cubes. We're going to break them today. We're going to do that in group order number. So if you remember in when we assign the groups, we have like a group 1, group 2, group 3, group 4. So we'll break group 1's cubes first, then group 2, then group 3, etc. So just have your lab sheets ready today, because I want to know what group numbers correspond to which mold numbers. So we'll do those in order today. Each cube will probably take like a minute or two. So there's 18 cubes. So do the math. That's about how long the lab's going to be today. So okay. Don't forget, homework 4 is going to be due next Tuesday. After today, though, you'll have a clear understanding of how to do it. Okay. Because it's the star of the show is the mix design. Okay, everybody get the code? All right, let's do it to it. Okay, so here is the design example. This is in the slides, and so I went ahead and just put it here in the notebook. So let's go through the data and the example with a fine-tooth comb together. Okay, so we're going to proportion a mix design, a batch of Portland cement concrete to be used in a bridge deck project. So to be clear, okay, I want everybody to have a clear understanding of what our final answer is. Okay, so our final answer is going to be something like this. Okay, that ain't going to work. So what I'll say is our final answer is for 1 cubic yard of concrete, this is how much gravel we're going to use. This is how much sand, this is how much Portland cement, this is how much water, this is how much admixture. That's our answer, okay? So we're trying to proportion the ingredients for a single batch, okay? And for the final answer, we'll probably report to the nearest pound, okay? Even though, like, we'll calculate it probably with more precision, okay? Now, a couple factoids about this project that are going to be important for our proportioning. We're going to assume that the bridge deck will be subjected to freeze-thaw, de-icing salts, and sulfates. It's an exterior application, so it's going to be exposed to the elements. If it's, let's say around here, it's going to be subjected to freeze-thaw cycles, and we're going to put road salt on the bridge in February and all that jazz. Okay? And so those exposure categories will become important when we start speccing things out throughout the mix design. These dimensions are going to be necessary for assessing our aggregate. So this is a bridge deck that's going to be 9 inches thick. So just to be clear, we're talking about the slab that goes on top of the beams on a highway bridge. Okay, so we're going to say that bridge or that deck is 9 inches thick. The cover the clear space between the edge of the rebar and the edge of the forms. We're going to assume that that minimum cover is 2.5 inches, and we're going to assume that there's 2.5 inches of space between rebar. Okay, and that's necessary to ensure that our aggregate can fit where it needs to go. Okay, now for this mixed design, we're going to target a compressive strength of 4,000 psi. So if you remember in step 1, this is what the structural engineer is going to use for design. So when we proportion our batch, we're going to proportion it for a little bit higher than that. Now, in order to do that, we need to assume a standard deviation of 400 psi. That's what we're going to assume from all of the cylinders that we test, and we're going to assume that we're going to test over 30 samples. Okay. The other thing that we need is data for our aggregate and our ingredients. Let's move Microsoft Teams. It has a way of just popping up at the worst time. Coarse aggregate, fine aggregate. So for the coarse aggregate, the gravel, we have a 1-inch nominal max aggregate size. It's sub-angular classified. Here's our moisture content. This is our absorption. So when I look at moisture content and absorption, I look at these two data points, and I see that this aggregate has excess moisture, right? It has more moisture than can fill the pores, okay? Same thing with the sand, the fine aggregate. The absorption is 0.9, the moisture content is 4.5. So this is really, really wet sand, okay? So the amount of water that we calculate, we're going to correct that. We're going to be dropping that water a little bit. The idea is, I'll make up some numbers. Let's say our mix says we need to put 200 pounds of water in there. Well, there's already a certain amount of water just in the aggregate based on the fact that the moisture content is higher than the absorption. So we're going to back that water off a little bit, okay? Got the specific gravities, got the fineness modules for the fine aggregate, dry rotted unit weight for the coarse aggregate. I know that we're using type 5 Portland cement and we're using an air entrainer. This seems complicated, but trust me, it's pretty easy. All right, ready to go? Let's do it to it. Okay, so let me, all right, let's do this. Okay, so okay. All right. So step 1. Okay. Step 1 is going to be to determine the required compressive strength. Okay. Okay. In other words, we're shooting for 4,000 psi. We're going to bump it up a little bit. Okay. We're going to bump it up a little bit to account for the fact that we're going to have statistical variability in the cylinders that we test. Okay, so let's take a look at our steps here. So first thing we've got to do is we've got to look at our standard deviation and our modification factor. Okay, so our standard deviation, what was the standard deviation of the samples that we're going to use? What were we told? There we go, 400 psi. What modification factor are we going to use? How do we determine that? Sample size. How many samples are we testing? So what's F? 1, right? So what we'll say, and so I'm going to hop back and forth between this PDF quite a bit. So F is 1.0. And I'll put in red that. So I'll put in red sort of my reasoning for why I'm doing what I'm doing. Okay? So S prime is going to be Fs, which is really just going to be 400 psi. So in other words, remember my standard deviation is a measure of how scattered my data is. And so what we're doing here is if we don't test a lot of cylinders, we don't have as much confidence in that standard deviation. So we bump it up a little bit with this factor F. Because we're testing enough samples, we really don't need to worry about that right here. Okay, so therefore, FCR is going to be the maximum of the following: FC prime plus 1.34 S and FC prime plus 2.33s minus 500. Or S prime, but it doesn't really matter in this case because it's all the same. So just plug and chug. Oh. All right, so help me out. What are we getting for the top row? Has everybody brought their Casio FX115ES Plus or similar scientific calculator with them today? What about this top row? What do we get for this? 4536. Do I have a second? Okay, how about the bottom row? I don't have this one computed, by the way. But I want you to do it for me. 4432. Do I have a second? Everybody good? Do I have a second? Is it? Okay. So that means that the maximum is that. Okay. Now I want to show you something that I'm going to do here. Okay. So I want you all to get into the habit of this with this process because this process is big. There's a lot of steps. Okay. At the end of step 1, we get a value. That value is FCR prime is that. I want you to box that. And I want you to strike a line. Okay? So in other words, like we do step 1, we get an answer, we move on to the next step. Okay? Because I want you to be able to easily identify what is the response from each step. Okay? Everybody with me on that? Okay. All right. Okay. So far, so good? Okay. Any questions about step 1? All right. Step 2. Step 2 is we need to determine our water-cement ratio. Okay? So what that means is we need to determine the percentage of water versus cement. Okay? Now the way that we're going to do that, and get used to this with this method, is we're going to look at tables. Okay, so let's look at table 7.1. Okay, now here's the thing. You go into table 7.1 with FCR, not FC prime. Or, you see what I mean? We're going in with this value. So we're going in with the value from step 1. What was the value from step 1 again? 45. So let's call it 4,500 just to keep things simple. All right. Now, are we going to use air entrained concrete or non-air entrained concrete? Let's talk about that. What should we use? What is the difference? Let's go back to that. Why do we have air? Like, why do we use air entrainer? First off, like, hold on. We are going to use air entrained concrete because I said we're using an air entrainer. But why are we using air entrainer? What does an air entrainer do? It puts the little bubbles inside the concrete. Why does that matter? Why does that matter for this problem? Because it's outside. It's subjected to freeze thaw. We want the concrete to have that wiggle room to expand and contract, and that's what the bubbles do. Okay? So yes, this is air entrained. Okay? So we're going to select based off of this column right here. Okay, so we're selecting based off this column. Now our FCR is about 4,500, so that means that we're selecting between these rows. So we select between these rows, air and train concrete somewhere around right here. We're only going to go to 2 decimal places. So what value you want to use? 0.44, right? Because for 4,000, it's 0.48. For 5,000, it's 0.4. We got about 4,500. Call it 0.44. Okay. So this is what we'll do. Table 7.1 will say FCR prime is 4536 psi. We'll say air entrained that means a water cement ratio of 0.44. Okay? That's where we're getting at. Okay? But we also have to check the other 2 expressions, the other 2 tables. Okay? So what's the deal with the other 2 tables? All right? Let's take a look at 7.3. Okay, 7.3, maximum water cement material ratios and minimum design strengths for various exposure conditions. So essentially what the American Concrete Institute is saying is, I don't care what you've got over here, these are your maximums based on given exposure categories. Okay, so let's take a look at our exposure condition. We have 1, 2, 3, 4. Let's read these through. Concrete protected from exposure due to freezing thawing. Does this one work? No, this is outside. This one's not going to work. Concrete intended to have low permeability when exposed to water probably doesn't make sense, especially since we're using type 5. But concrete exposed to freezing thawing in a moist condition or de-icers, this one probably makes sense. This one doesn't, because we're not being exposed to brackish water, seawater, or spray from these sources. We didn't say this was going to be in Miami. We'll assume it's here in West Virginia. So we're going to have concrete exposed to freezing and thawing. So our maximum water cement ratio is 0.45. Okay, so let's write that down. So table 7.3. So we'll say condition 3. Let's do it like this. Let's just say WC max is 0.45, but for like the assumption, we'll call that condition 3. Okay. So notice how, like, I'm trying to write in red if there's any assumptions that go into the tables. Okay. Any decisions that I made. I didn't make a decision about FCR prime being 4,500 because I calculated it. All right. Now what about this table? 734. These are going to be our water cement ratios, our maximum water cement ratios based on sulfate exposure. Okay. What did we say for this deck? Did we say, what, severe sulfate exposure that we were going to assume? So we're going to say severe sulfate exposure. In severe sulfate exposure, we're going to use type 5 cement, which we are. We're going to have a maximum water cement ratio of 0.45. Okay? So with this table, we're also getting a maximum water cement ratio of 0.45. Okay. Now let me ask you a question. Okay, so I have this water cement ratio from table 7.1, and I have these water cement ratios. Now the question is, which one am I actually going to use? Like, in other words, I want to be able to strike a line and be done with this step. Okay, so in order to do that, I need this equals something. Okay, so let's have like a Let's talk about the idea. Let's talk about the concepts. if I'm designing a water or a batch of concrete, is it desirable for the purposes of strength to have a high water cement ratio or a low water cement ratio? Say it again? Low, right? Because the more you up your water, the lower the strength, right? So essentially what I want to do is choose the lowest value possible, okay? So my answer in this step is going to be 0.44. So long story short is, from this step, I want to choose the minimum possible. It is possible that whatever I calculate here, I'm cut off by these maximums, okay? But really all these maximums are saying is from these, take the smallest one. Okay? Does that make sense? Okay. This is good stuff. All right. So far, so good? Okay. Step 3, okay? So step 3 is going to be our discussion about the gravel. Okay. So let's talk about the gravel. All right. So let's pull up our little handy dandy guide here. First thing we're going to do is we're going to talk about this. To be candid, this part actually really has nothing to do with the mix design. We could skip this and just do the mix design. But we're going to check this because we're civil engineers, okay? And what we're going to do is make sure that the aggregate that we're using is appropriate for the application, okay? Now, what were we given about the aggregate at the very beginning of the problem? We were told that the nominal max aggregate size is 1 inch. Remember, the nominal max aggregate size is basically the first sieve that starts to retain some meaningful aggregate, right? Okay, so we can get that from a sieve analysis. So what I'm going to do is I'm going to do a little box here, because it's essentially a check by itself, but we're going to do it, okay? I can do better. Okay, so let's look at our clearance requirements. Now, what is the difference between a nominal max aggregate size and a max aggregate size? In other words, if I know this, what is my max aggregate? Say it again?
1.5.
Yes, it's one size higher, right? So whatever the nominal size is, the maximum aggregate size is one size higher. In this case, 1.5, which I'm getting that, you know, just right here. I've got my standard sieve sizes listed. So if that's 1 for the nominal max, we go 1 step higher, okay? Now, what we're going to do is check every clearance requirement that makes sense here, okay? So which ones make sense? So we're doing a bridge deck, okay? Do we check the form dimensions? Yes, because we are going to put the concrete in forms, right? Are we going to check the clear space between the reinforcement? Yes, because we know the bar spacing. Are we going to check the clear space between the reinforcement and the form? Yes, because we know the cover. Are we going to check the unreinforced slab requirement? No, because we're putting rebar in the slab, right? So we're going to check all of these except for the last one. So let's walk through that, okay? All right, too many windows. Okay, so let's look at the form Okay, so for the form, it is, I mean, what's the form requirement here? It is 1/5 of the minimum clear distance, okay? Which essentially is just 1/5 of the thickness of the slab, okay? So that's going to be 1/5, and the slab was what, 9 inches thick? I think I can do that in my head. That's 1.8 inches. Okay. We have our bar spacing. Now, what's our bar spacing limit? Our bar spacing limit is 3/4 of the clear space, and the same thing here, 3/4 of the clear space. Okay. So, what was our bar spacing? 2.5 inches. What is that? 3/4 of 2.5. Okay, we'll call it 1.9. And our cover that's also going to be 1.9. Okay. So, like, just to be clear, here's what's going on, right? So, we've got let's say this is our plywood, okay? And this is our concrete slab, right? So it's 9 inches thick, right? Okay? And we're going to put rebar in here. Actually, hold on. Do this. I think I can make that a little bit better. Let's just do that. That's close enough for the purposes of the discussion. Okay. And what I'm saying is that this dimension here is 2.5 inches, and this dimension here is also 2.5 inches. Okay? And what I'm saying is that for these dimensions, there are limits on how big the chunks of aggregate can be. In other words, if I had a chunk of aggregate that's like this big, that would be a problem, okay? Because it couldn't fit under here. It couldn't fit under here or fit between these bars, right? So what I'm saying is that these are my limits, okay? But is this a problem for this concrete? No, because all of these values are greater than 1.5 inches. So therefore, we are good, okay? So if our aggregate was bigger than these, we'd have a problem, okay? Does that make sense? Yes.
What dimension is the form?
That is the thickness of the slab.
Okay.
Yeah, so basically what that's saying is just like, you know, if you have a, whatever box that it's going in, you know, like let's say you're doing like a column and you have some aggregate in there, that it's got to be 1/5 of that dimension. So in the case of the slab, I mean, the slab's probably like 40 foot wide or 100 foot long, but it's only 9 inches thick, so I'm using the smallest one. So, good question.
Oh, so you're saying since the aggregate is a 1.5 max aggregate, so it can all fit in between those things? Okay.
Yes, yes. I want this to be smaller than all these. If it's bigger, that's a problem. That means the aggregate's too big. This is a good discussion. I'm glad we're having this. Now, this doesn't really have anything to do with actually figuring out step 3, but since we're talking about coarse aggregate, it makes sense to go ahead and do it now. Everybody good? Now, one thing, I put this in a box. This box is the only place that the max aggregate lives. We're using nominal max aggregate for the rest of the exam. Okay? No more max aggregate. Okay. So the max aggregate stays in the box. Okay. All right. Rest of this, I think, is pretty straightforward. Okay, so the real goal of this step is to figure out how much gravel is going into our mix. Okay, so let's go through that. So how do we figure that out? We figure that out with Table 7.5, and essentially what Table 7.5 is saying is that we figure out how much gravel goes into our mix as a function of how big the nominal max aggregate is and how fine our sand is. Okay? So the idea is that if our sand is more and more fine, right, the idea is we don't need as much gravel because the sand will fill up the spaces. Okay? Now, so for this problem, what is our nominal max aggregate size again? 1 inch. And what was our fineness modulus? 2.7. Okay? So we have a nominal max aggregate size of 1 inch. Okay? And our fineness modulus is 2.7. So this is our value for 2.6. This is our value for 2.8. What should we use? 0.68. Okay. So what we'll do is we'll say Table 7.5. We'll say 1 inch nominal maximum aggregate. And we'll say our fineness modulus is 2.7. So that means we have a factor of 2.70. And I call that C sub S. Why? I don't know. Seemed like a good symbol. Got to call it something. Okay. Or wait. Nope. I'm falling behind. 0.68. Whoops. Yep. So in between that. Okay. Essentially what this is the percentage of volume that is going to be occupied by gravel. Okay? So how do I figure out the weight? Well, it's pretty simple. I'm trying to figure out the weight in a cubic yard. Okay? So if I take the unit weight of the aggregate, multiply it by 0.68, that'll tell me the amount of aggregate in a cubic foot. I then multiply it by 27 to get the amount of aggregate in a cubic yard. Does that make sense? Pretty straightforward. So, therefore, my weight of my gravel is going to be the unit weight of the aggregate times however much of it is going to go in this mix times that conversion factor to get it into pounds per cubic yard. Okay? So this is going to be, what was the unit weight for this problem? 108? So if this was 1, then like all of the concrete would be coarse aggregate. Obviously it's not because we got gravel, sand, cement, and water, but that's kind of the idea. So when we chug this out, what do we get? Second? So I propose for a single cubic yard that's how many pounds of gravel we need. Now, this is not our final answer for gravel. Okay? In fact, we're going to change this answer in our very last step. Okay? Because what we're going to do is tweak this number a little bit to account for the fact that the gravel has some moisture in it. Okay, so the idea is we're going to get a weight of a weight of gravel, a weight of sand, a weight of cement, a weight of water, and at the very end, what we're essentially going to do is we're going to back off the water a little bit because we've got excess water because of the moisture content versus the absorption. So we're going to back off the water, but we're going to add a little bit of gravel and sand to compensate. So this number will go up just a little bit at the very end. Okay. Sound good? All right, step 4. Bear with me, we're getting there. Step 4. So, our required air content. Okay. Okay. So let's talk about our exposure conditions. So we're not going to use air and train or non-air and train concrete. We're use air and train. Or we're going to do mild, moderate, or severe. Mild would be indoor, not exposed to freeze or thaw. That doesn't make sense. Moderate, some freeze thaw, but no moisture before the period of freezing, no salt. Doesn't really make sense. Severe is for us, right? That's for our application. So we're going to use severe exposure, right? Severe exposure, 1 inch nominal max aggregate. We're going to have a percent air of 6%. Does everybody see that? Okay. So what I'll say is, oh, hold on. Table 7.6. Did I get that right? Table 7.6, yeah. Okay. So let's go with 1 inch nominal max aggregate. Let's go with air entrained. Severe exposure. And we get that our percent air is 6%. So that's it. That's all we get from that step. Bless you. Okay. Short step. Okay. Step 5 is our workability, essentially our slump, okay? I'm going to call a little bit of an audible on our calculation because I had my calculations done a little differently, and I'm going to call an audible, so, because I'm going to make this interesting. Okay, so determine workability requirements. So this is our recommended slump for various types of construction. We're doing pavements and slabs, so we want our maximum slump to be somewhere between 3 inches and 1 inch, okay? Let's go with 2, okay? I put 3 here on my calculations here, but let's do the middle. Let's go with 2, okay? So let's keep our slump in between, so let's do 2 inches. So let's see what happens. So I'm going to need your help on this one. Yep. Yep. So again, I kind of want you to get into the habit as you do these steps that at the end of each step you get an answer, all right? So at the end of step 4, we have a percent error. At the end of step 5, we have a slump, okay? So at the end of each step, I want an answer. Okay. So step 6. All right. Step 6 is going to be looking at our water, the amount of water we're going to put into the mix, okay? Okay. So let's take our time with this. Okay. Now, let's just sort of digest what we have here for step 6 because we're determining the weight of water. We have our weights that are presented for angular aggregates. And then we have corrections at the bottom for if we have different angular shape or different shapes other than angular. What is the shape of our aggregate? Subangular. So we're going to have to apply this correction. Okay? So let's see what we got here. So our slump. Okay? So our slump we have from 1 to 2, 2 to 3, 6 to 7, 1 to 2, 3 to 4, 6 to 7. And the difference is this is non-air and train, this is air and train. So we're going to be down here in this air and train section, 1 to 2. So we're going to go off of this row right here. My solution went off a different row, so we're off script today. Okay, so we're off of this row. We're on a 1-inch nominal max aggregate, so that means our water weight is 270 pounds. Does everybody see that? So remember, we use the values in percentages. So we'll say table 7-8. So we'll say, again, that nominal max aggregate you use all the time. So we'll say that the weight of the water was 270. Okay? But I've got to correct that. Okay? And so my correction for subangular is going to be 20, right? So what we'll do is reduce that water content a little bit. So we'll say reduction. Scroll this up a little bit. So this was my initial weight of the water. I'm correcting it by reducing it 20 pounds. So this is 250. There's our water weight. Okay? And again, I'm just sort of expressing the weights just as pounds. I'm not really worried about the pound per cubic yard because at the very end my answer is here's how much is for a single cubic yard of concrete. So it's already going to be baked into the answer. Okay. Sound good? Yes.
If you had a slump of 5, just because that's not listed on there, would you take the average of the 2 rows or the?
That's a great question. That's a great question. So the question was just to make sure the recording gets it. If you have a slump in between, do you linearly interpolate? No. Go up to the next highest one.
Okay.
Ultimately, at the end of the day, you do want to default to the concrete being more workable. So, and again, we're going to correct for moisture anyway. So, okay, great question. All right. So, what did we calculate in step 2? What did we get out of step 2? What was the answer? But what was it?
Water ratio.
The water-cement ratio, right? So step 2 yielded a water-cement ratio. Step 6 yielded a weight of water. So why don't we calculate the weight of cement? You know, so that's what we're doing in step 7. Okay. So step 7 is the cement. Okay. I have my old dance move too. So. Okay, so from step 2, we got that the water-cement ratio was 0.44, and we know that the weight of the water is 250 pounds. So therefore, it's pretty easy What do we get for this? And I have no idea, excuse me, because this is not what I did here. So we are off the beaten path on this one.
568.
Say it again.
568.18.
Do I have a second? Okay. So 568.18. Okay. Now we need to check our limits. Okay. So we always have limits for stuff like this in certain exposure categories. So if I scroll down here, what are my limits? Okay. So we have two. We have an ACI minimum for flat work, and we have PCA minimum weights. Let's look at the PCA minimum weights. This is for from the Portland Cement Association. So we obviously don't need to apply for underwater applications, but I would argue this is a severe exposure category. We've been using severe throughout the whole problem. So we do have from the PCA a limit of 564. Okay, so. And this is a minimum. Okay? Now what about table 7.9? So let's take a look at that. So table 7.9 is the ACI minimum for flat work. Okay? Would that apply to us? I'm going to say yes, because what we essentially are casting is a slab. It is a large flat cast as opposed to like a column or a beam or some sort of mass concrete placement. This is a largely flat placement. So for a nominal max aggregate size of 1 inch, we have a minimum of 520. Okay? So we're going to go ahead and indicate that. There's that 1 inch nominal max aggregate. It's popping up again. So, from these, so the idea is if we want to drop the amount of water that we use, we want to use the minimum amount of water. For the purposes of strength, we want to up our cement. So we kind of want to use the biggest cement that we can. So in other words, our weight of cement, we're going to take that as 568 pounds. Okay, and again, we're going to take that as the just to the nearest pound, which is fine. Okay, we are mixing concrete. Okay, we're not. I mean, it isn't spinal surgery. So, hey, so okay. All right, sound good? Okay. Step 8, bless you. So one of the things about this method is that I'm calling it a refined method, but this is sometimes called a volumetric method, because essentially what we're doing at the very end is, so we're computing the weight of water, cement, gravel, air. Our final ingredient is going to be the sand. And the way that we compute the weight of the sand is we basically figure out all these different components occupy this much space. So the sand's got to occupy the difference. So we take all of those sums, or the sum of all that volume, and figure out the difference between 27 cubic feet and that. So we're doing it based off volume. So what volume component are we missing? We've got the gravel, we've got the cement, we've got the water, the air. We haven't talked about that yet, so let's do the air. Okay, so what step was it? Was it step 4? What was step 4 that we got the percent air? What was the percent air for this problem? 6, and that came from step 4, so. %. Okay. We have the weight of the cement from step 7. And that is 568 pounds. Okay. And what do we know about the admixture that we are using? The admixture says that we use 0.1 fluid ounces for every 100 pounds of cement, and for every 100 pounds of cement that we use 0.1 fluid ounces, we'll get 1% air. So we need to figure out how much admixture we're putting into our batch, and it's really easy. So therefore, the amount of admixture we put in is really easy. So what we're going to do is we're going to say .1 fluid ounces will give me 1% air. I need 6% air. Okay? Now this will work for 100 pounds of cement, but I'm not putting 100 pounds of cement in this thing. I'm putting how much? 568 pounds? And there we go. Okay? And again, this formula is pretty straightforward. I mean, I even just reported it, right? Just take your rate, multiply it by the percent air, times the weight of the cement, divided by 100. It's really not that challenging. It's pretty straightforward. So, again, we're flying off the radar here. So what do we get for this? 3.41. Say it again. Do I have a second on that? Okay, so we'll call that .4. Okay. 2 more steps. And if we don't finish step 10 today, we might pick it up Thursday, because I don't want to rush this. Okay. All right, so step 9 is the sand. Okay. All right, I like doing this in a table, so let's draw ourselves a big table. Okay. Okay. So I'm going to list my ingredients. It's like I'm baking a cake. All right. So what goes into a batch of concrete? Gravel, sand, cement, water, and air, right? Essentially for this batch of concrete. All right. So we figured out the water. We figured out the cement. We figured out the gravel. We figured out the air. We are still working on everything else, which is everything else is the sand. Okay. Let's write down the weights. Okay. So what do we get? What have we done so far? The weight of the water. What was that? 250? Is that what we got? We got the cement. What was the cement? 568. The gravel, I think I had 1982-88. Let's call it 1983. Now, the weight of the air doesn't matter. Because, well, I don't really have any. Okay. All right. Let's now look at the specific gravity. What is the specific gravity of water? 1, right? What is the specific gravity of Portland cement? 3.15. Now the gravel, that's going to change. That's going to change from problem to problem. But we have that data. 2.665. That was given at the very beginning. That doesn't matter. Okay. Okay. So now we need to calculate the volume. Now how do we do that? The volume's pretty easy. Okay? The volume's pretty easy because all we have to do is take the weight over the unit weight of the material, right? Remember, unit weight is weight over volume, so volume is weight over gamma. Well, gamma is going to be the unit weight of water times the specific gravity. And what is the unit weight of water, by the way? Pounds per cubic foot.
Yeah.
Am I bringing up fluids topics that you don't want to bring up? Well, sorry. What's that?
That I wish I knew.
Oh, come on. The unit weight of water is 62.4 pounds per cubic foot. Okay, so let's take the weight of the water. So how do we calculate this first row? So we take 250 divided by that times 62.4. So what is this divided by 62.4? Let's say 3 decimal places. I heard that second. Okay. How about this one? 568 divided by the product of that and 62.4. What's that?
2.889.
I don't have these numbers. This is all y'all. So.
I think it's 890. Yeah.
890. Okay. All right. This next one, 1983 divided by the product of that and 62.4. What do we get for that? Second? Okay. Now, I don't have a weight of air and I don't have a specific gravity of air, but the volume of air is really easy, okay? Now, I propose that the answer is just 1.620, okay? Now, if you're asking, where did I come up with that? It's pretty easy. It's just 6% of 27 cubic feet. Because that's how much air is in the batch, right? I mean, it's a volume of air, right? So that's why you don't need that or that. It's just, that's it. So, now, so how much volume does all this occupy? 20.441. Do I have a second? So the water, cement, gravel, and air occupy this much volume, okay? If that is the case, then therefore, the volume of the sand is just 27 minus this. This is why it's a volumetric approach, because at the end, we're determining the amount of our final ingredient based on this. Okay? So what do we get for that? Sound good? And if we have the volume of the sand, we can therefore get the weight of the sand by taking the volume of the sand times its unit weight. What is its unit weight? It's specific gravity times the unit weight of water. Okay? So, what was its specific gravity? 2.559 or 599? Did I get that right?
Yeah.
Yep, right there. Well, I'm scrolled over, but okay. So what do we get for this? Again, I need your help on this one.
1063.7.
1063.7. Do I have a second on that?
Yeah.
Okay. So our weight of the sand is that. Does that sound good? Okay. So let's take stock, because I think we can knock this moisture correction out pretty quickly. Let's take stock of where we're at. We have a weight of gravel, a weight of cement, a weight of sand, a weight of water, and the amount of admixture. Aren't we done? No, there's one thing left to do, and that's the moisture correction. Because remember, this was really soggy sand, so there's already water in the sand. If we don't correct for that, our batch is not going to be properly proportioned. So the last step is our moisture correction. Okay. Let's look at our moisture correction. This is another one of those, I like to do this in a table, okay? And so we're doing our moisture correction for the coarse and fine aggregate, okay? So what I'll tell you is that in step 10, the gravel, the sand, and the water are going to change. But the cement is not. The air entrainer is not. So whatever we got for the weight of cement, whatever we got for the air entrainer, that's it. We're not changing that. It's everything else that we're changing. Okay. So let's take a look at our aggregates. Okay. So we have weights. And remind me, this was 1983. What was this? We just calculated that. 1064. Okay. Okay. So first thing I'm going to do is I'm going to look at saturated surface dry. Okay. So I'm going to assume that all the pores are full and the surface is dry. Okay. So I need the absorption of each aggregate. What was the absorption of the gravel and what was the absorption of the sand?
0.51% on the gravel, 0.9% on the sand.
So actually, hold on. Okay. So I have the absorption. So let's take the gravel. I have 1,983 pounds of gravel. Okay. If 0.51% is the absorption rate, how much water is in the gravel? How do I figure that out? It's pretty easy. All I do is I take the weight times A over 100. So what do I get for this and this? And let's say 2 decimal places.
10.11.
Okay, and this one.
9.58.
Second?
Yep.
Okay. So this right here is saturated surface dry. Okay? So for this amount of gravel, I propose that the surface is dry but the pores are full. It's got 10.11 pounds of water inside the aggregate. Everybody okay with that? That's if it's saturated surface dry. But it's not saturated surface dry. This gravel and this sand are soggy. They're moist. They have excess moisture. What is the actual moisture content of the gravel and the sand? What was this and this? This was 1.69 and 4.50. So what is the weight of the water here and here?
£33.51 for gravel.
Second?
Yes.
And for the sand? Second? Okay, so here's my point. Okay, this is how much water is in the gravel if the pores are completely full but the surface is dry. But this is how much is actually existing. So, is there excess moisture in this gravel? Yes or no? Yes, because there's more water here than there is here. What is that excess moisture? We'll call this delta W. So how do we determine that? We just take the difference of this and this. So for that first one, we're going to get plus 23.40 pounds. What about this second one? I need your help with this one. 38.30. So if I were to sum this, what would I get? Is that 0.7, 1, 6? Did I get that right? 61.7 pounds? I mean, did I get that right? So, I want to be clear what this means. This is what I'm saying. If you have this stockpile of gravel and this stockpile of sand, put it in a bucket. Don't get a 5-gallon bucket of water. Just take this amount of gravel, this amount of sand, stick it there. I propose that there's already 61 pounds of excess water just in the aggregate as is. Now, what did we say we were going to add? How much water did we say we were going to add to the mix? 250 pounds? Think about what we're doing here. We're going to add 250 pounds of water to a batch of concrete that already has 61 pounds of water in it before we even do anything. Does that make sense? We got to take that off, okay? So what I am saying is that our weight of water final is our weight of water initial minus delta W. In other words, this is 250 pounds minus 61.7 pounds, which is what? Say it again.
188.3.
Everybody okay with that? Okay. Now, so what we've done is we've dropped the amount of water. We also have to correct the amount of gravel and sand, but that's pretty easy. Gravel. So the weight of the gravel and the weight of the sand final is just going to be the weight, the initial weights, times 1 plus the water content. So essentially what we're going to do is we're going to take 1983. This one's going to be, what is it, 1.0169. This one's going to be 1064. And this is 1.0450. So in other words, this was 1.69% moisture content. This was 4.5% moisture content. So just this value, like here and here, just as a percentage, or as a decimal. So take that divided by 100, add here. Take that divided by 100, add here. So when you chug this out, what are you going to get?
2016.51.
And this one?
1,111.88. No, it's 1111.
1111. Like that. Second? Okay. Therefore, and then our cement was 568. and our admixture was, what was it, 3.4. Whew. That's a problem. That's a problem and a half. But that, ladies and gentlemen, is how you do it, okay? So, again, all we're doing is we're basically using our exposure categories. We're using our nominal max aggregate size and our lab data to determine volumetric proportions of each component. The sand is what we figure out last, but on a volumetric approach. And then at the very end, we correct for moisture, okay? Usually what that means is dropping the water, adding the gravel. All right, we take a step back. Does this make sense? There's a lot we did today, but the homework assignment is very much like this, just different parameters, different problems. So I suggest you take a look at it, and Thursday, let's just see where everybody's at. I promise Thursday, much lighter on the math side of things, much lighter. Let's pack up, we'll go down to the lab, break some stuff.
I know.